Tonight we're going to drift through the first light of the early universe and stand on the edge of the impossible. No one expects the dawn of time to be crowded, yet we find massive cities of stars where there should have been only a cold fog of hydrogen. This is the paradox of mature galaxies, existing just a few 100 million years after the Big Bang, appearing in the deep infrared as heavy luminous anchors in a void that was supposed to be empty. Picture the scale of this silence. You are floating in a darkness so absolute that the concept of direction ceases to exist, suspended in a vacuum where the temperature hovers just above absolute zero. The cold is not merely a lack of heat, but a physical presence, a heavy weight pressing against the edges of existence. In every direction there is nothing, no stars, no planets, no beacons of light, only a thin, ghostly haze of primordial gas, stretching across billions of light years in a featureless expanse. This was the expected state of the infant cosmos, a slow and lonely beginning where the first sparks of light would take an eternity to flicker into being. But as we glide deeper into this prehistoric dark, a glimmer appears. It is not the faint, flickering light of a single lonely star, but a concentrated, blinding brilliance. As you draw closer, the light resolves into a structure of impossible proportions. You are seeing a galaxy, but not the kind of chaotic, fragmented cloud of gas predicted by every model of cosmic evolution. This is a city of stars, a dense and rotating metropolis of stellar mass, humming with the energy of a billion suns. It is structured, it is massive, and it is existing in a window of time where it simply should not have had the time to form. The light hitting the sensors of our instruments has traveled for over 13 billion years, crossing a continent of emptiness to tell us that the early universe was not a vacant desert, but a place of sudden, violent efficiency. The sheer weight of these objects is what defies the logic of the old maps. In the standard timeline of the cosmos, gravity is a patient architect. It takes millions of years for gas to collapse into the first stars and hundreds of millions more for those stars to congregate into small, irregular clumps. These clumps then merge slowly and painfully over eons to build the great spirals and ellipticals we see in our own neighborhood. It is a process of slow accumulation, a cosmic masonry where each block is laid with agonizing precision over billions of years. But here, at the very edge of the observable horizon, the masonry is already complete. We are seeing finished cathedrals of light where we expected to find only the first few scattered bricks. The light from these ancient systems is shifted deep into the red, stretched by the expansion of space itself, until it becomes invisible to the human eye, a silent whisper that shook an entire field of astrophysics. We are looking at a version of reality where the universe filed each event in space-time with a speed that contradicts our understanding of gravity. These galaxies are not merely present, they are mature. They possess a gravitational grip so strong that they pull in surrounding matter with a hunger that suggests a massive hidden core. They are anomalies of scale, titans born in a cradle that should have been too small to hold them. As you drift further into this infrared glow, the feeling of displacement grows. You are witnessing a contradiction written in the stars. The numbers do not line up. The mass of these early galaxies is so great that they should have required a reservoir of gas larger than the entire local volume of the early universe to assemble themselves in such a short window of time. It is as if we opened a history book to the first page and found a fully developed civilization already inhabiting the land, with cities and laws and architecture before the first seed had even been planted in the earth. This is not a gentle discovery. It is a reversal of the consensus. For decades, we viewed the early universe as a blank canvas, a quiet dawn where the first light was a tentative, flickering thing. We believed we understood the pace of the cosmic clock. We believed that complexity was a reward for patience, a result of billions of years of collision and collapse. But the evidence appearing in the deep field tells a different story. It tells us that the early universe was capable of leaps of complexity that bypass our current mathematical models. It suggests that the void was not as empty as we thought, and that the laws of assembly worked with a terrifying speed in the first few 100 million years. You are now floating in the wake of these impossible giants. Around you, the darkness is still vast, but it is no longer silent. It is filled with the radiation of these first massive systems, their light acting as a postcard from halfway across the observable universe. The scale of the distance is impossible to process. If the distance from the Earth to the Sun were a single grain of sand, the distance to these galaxies would stretch beyond the horizon of the world, and yet they are there, staring back at us through the lens of the most powerful eye ever built by humanity, challenging every assumption we held about the origin of structure. The tension between what we expected and what we see is the engine of this mystery. We are staring at a cosmic crime scene where the evidence contradicts the witness. The witness is the standard model of cosmology, the map that has guided us for half a century. The evidence is the light, cold, and ancient, proving that the first galaxies were not the shy, stunted infants we imagined, but mature monsters of stellar mass. This revelation does not just change a few numbers in a textbook. It forces us to rethink the very nature of how matter organizes itself under the influence of gravity. As we linger here in the iridescent glow of the first light, the silence of the vacuum feels different. It is no longer the silence of nothingness, but the silence of a secret. We are standing on the edge of a revelation that suggests our timeline of the universe is missing a chapter, or perhaps that the chapter we have is written in a language we have only begun to decode. The early universe was not a slow climb out of the dark, but a sudden blinding leap into existence. But to understand why this is impossible, we must look at the map we thought was final. Expectation, a slow and methodical dawn of structure. This was the architecture of our understanding for decades, a blueprint of the cosmos that felt certain. To look back at the beginning was to look at a period of patience, where the universe took its time to wake up. We believed the first stars were lonely, flickering candles in a vast, freezing ocean of hydrogen, appearing one by one in a tentative dance of gravity. The map we followed suggested a gradual assembly, a cosmic patience where small, chaotic clumps of gas would drift together over eons, slowly merging into the first primitive galaxies. These were not meant to be the grand spirals we see today, but stunted, irregular fragments, shattered pieces of light that lacked the weight and the grace of a mature system. This vision of the early universe was anchored in the standard cosmological model, a framework that dictated the pace of everything. It predicted a steady, rhythmic buildup of stellar mass where gravity acted like a slow sculptor, carving out the first structures from the void over billions of years. The logic was simple and elegant. You cannot have a city without first having a few houses. You cannot have a massive galaxy without first spending an eternity gathering the raw materials of gas and dust. The universe had to earn its complexity. It had to struggle through a long infancy of darkness and cold before the first true galactic hubs could emerge. This expectation was formalized and reinforced by the work of astronomers like Maddow and Dickinson in their 2014 paper on cosmic star formation history, published in the Annual Review of Astronomy and Astrophysics. Their research provided the baseline for how we viewed the growth of the cosmos. It described a curve, a rise and fall of star formation that peaked billions of years after the Big Bang. According to this map, the very early universe was a place of scarcity. It was a time when the rate of star birth was low, and the objects being born were small, fragile, and fleeting. The 2014 data suggested that the early dawn was a whisper, not a shout. It told us that the massive luminous galaxies that dominate our modern sky were the result of a long, arduous climb, a process of accumulation that required the steady passage of deep time. We accepted this timeline because it fit the math. We believed that the first few 100 million years were a period of preparation, a time when the universe was merely setting the stage. We imagined the first galaxies as scattered sparks, barely clinging to existence, drifting in a void that was still too hot and too chaotic to support the birth of giants. In this version of history, the cosmos was a student of patience. Matter drifted, collided, and settled in a slow-motion ballet, with each new generation of stars adding a thin layer of complexity to a world that was mostly empty. There was no room for monsters in the infancy of time. There was only room for the small, the dim, and the disorganized. This was the comfort of the consensus. It gave us a linear story of progress. We saw the universe as an entity that grew in proportion to its age, moving from simplicity to complexity in a predictable arc. We looked at the distant reaches of space through our older telescopes and saw exactly what the models told us to see: a dimming of light as we peered further back, a thinning of the crowd as we approached the beginning. The deeper we looked, the smaller the galaxies became, confirming the idea that the dawn of time was a quiet, lonely place. We were convinced that the universe had a speed limit on its own evolution, a biological clock for galaxies that could not be rushed. The Standard Model promised us a slow sunrise. It told us that the first massive galaxies were the elders of the cosmos, products of a long and weary journey of mergers and collisions. We believed that if we looked back to only 500 million years after the start, we would find nothing more than a cold fog of hydrogen and a few scattered infant stars. We expected a wilderness, a primal state of existence where the very concept of a massive galaxy was a physical impossibility. The gravity of the time simply wasn't supposed to be strong enough, the gas wasn't supposed to be dense enough, and the clock hadn't been ticking long enough to produce something of scale. For years, this was the only story that made sense. It was the map that every astrophysicist carried, the baseline against which all new observations were measured. We were not looking for giants in the dark because the laws of physics, as we understood them, forbade their existence. The universe was a slow-burning fire, and we believed we knew exactly how long it took for the first sparks to become ablaze. We had the papers, we had the simulations, and we had a cohesive theory that explained the growth of everything from the first atom to the Milky Way. And yet the universe has a habit of ignoring our maps. The silence of the deep infrared was hiding a truth that the Standard Model could not account for. We were staring at the horizon of time, believing we saw a blank canvas, unaware that the canvas was already crowded. We were waiting for a slow dawn, not realizing that the sun had already risen in places we couldn't see. The gap between our expectation of a stunted infancy and The reality of a premature maturity was about to become a canyon. We remained in this state of confidence, leaning on the 2014 consensus and the predictions of the Standard Model, believing that the early universe was a place of quiet beginnings. We were content with the idea of a methodical, gradual buildup of mass. We felt we had decoded the rhythm of cosmic growth, but the rhythm was wrong. The pace was faster than the math allowed. The universe had cheated the clock, creating structures of immense weight and complexity in a fraction of the time we thought was necessary. The evidence was there, floating in the deep infrared, shifted far beyond the reach of our previous eyes. It was a ghost signal, a whisper of mass that defied the 2014 history of star formation. It was the signature of something that should not exist, massive, mature galaxies appearing in a window of time that should have been reserved for gas and dust. The map was not just incomplete, it was fundamentally wrong about the scale of the beginning. Until a golden mirror shifted our gaze into the deep infrared reality, a cosmos that defies every map we ever drew. When the James Webb Space Telescope finally opened its golden eye to the deep infrared, it did not find the stunted, fragile seedlings the 2014 models predicted. Instead, it found titans. The instrument looked back into the darkness, peering through the dust and the distance, and it saw something that should not exist. It saw fully formed, massive galaxies residing in the absolute infancy of time. In a 2023 paper published in Nature, a team led by Ivo Labbé identified a population of candidate galaxies that shattered the previous consensus. These systems appear just 500 to 700 million years after the beginning of everything. In the timeline of the universe, this is a mere blink, a fraction of a second in cosmic terms. According to the old rules, these galaxies should have been small, chaotic clumps of gas, barely beginning to coalesce. They should have been whispers of light. But the data from Webb told a different story. These were not whispers. They were screams. Labbé and his team discovered what are now known as the impossible early galaxies. These are systems with stellar masses exceeding 10 billion suns. To understand the gravity of this discovery, we have to look at the math of growth. To assemble 10 billion suns worth of stars in only a few 100 million years, the universe would have had to convert gas into stars with a efficiency that borders on the impossible. It would require a rate of star formation that exceeds anything we have ever observed in the modern universe. The reality is that these galaxies were already mature. They were not slowly growing. They were already there, heavy and bright, occupying a window of time that should have been reserved for the cold fog of hydrogen. The Standard Model of cosmology suggests a gradual climb, a slow accumulation of matter where small things merge to become larger things. But the JWST observations show a shortcut. These galaxies did not wait for the slow process of merging. They appeared as giants, fully clothed in stars, standing in a void that was supposed to be empty. This is the core of the paradox. We expected a slow dawn, a gradual awakening of light across the void. Reality gave us a sudden, violent eruption of complexity. The 2023 findings from the Nature paper suggest that the early universe was far more productive and far more aggressive than our simulations ever allowed. The galaxies found by Labbé were not outliers or anomalies. They were a population, a group of massive systems that suggests the very first era of the cosmos was a period of unprecedented architectural speed. We are seeing a universe that cheated the clock. The sheer weight of these galaxies, those 10 billion solar masses, acts as a physical contradiction to the theories of the previous decade. If these galaxies exist, then the rules of how gas cools and collapses into stars must be rewritten. The efficiency of the early cosmos was not a slow burn, it was a flash. The structures we see are too heavy for their age, too stable for their youth, and too massive for the amount of time that had passed since the Big Bang. The James Webb Space Telescope has effectively moved the goalposts of astronomy. It has shown us that the early universe was not a quiet nursery, but a forge of immense power. The gap between the expectation of a stunted infancy and the reality of these premature giants is a canyon of missing knowledge. We are looking at objects that possess a complexity and a mass that should have taken billions of years to assemble, yet they are present at the very start. Every single one of these massive galaxies is a piece of evidence that the early universe operated on a different set of priorities. While we waited for the first sparks to slowly become a blaze, the universe had already built cities of stars. These impossible galaxies stand as beacons of a hidden process, a mechanism of creation that we have yet to name. They are the heavyweights of the deep infrared, anchors of mass that pull at the threads of our understanding. The measurements are clear, the light is real, the 10 billion solar masses are there, etched into the data streams coming back from the Webb study. The map is no longer just incomplete, it is being discarded. We are now standing in a reality where the dawn of time was crowded with titans, where the void was filled with light far sooner than we ever dared to imagine. To grasp the weight of these objects, we must translate the numbers into a physical sensation. To understand the scale of this impossibility, we have to move beyond the numbers and feel the physical displacement of these objects. For decades, our mental map of the early universe was a sketch of fragility. Expectation was a cosmic landscape of scattered grains of sand, tiny flickering clusters of a few thousand stars drifting in a vast, lonely ocean of hydrogen. We envisioned a slow, tentative process where gravity had to fight for every single atom, pulling together small knots of matter that would take eons to grow into anything resembling a galaxy. In that old map, the first few 100 million years were a period of stuttering starts, a time of fragility and emptiness where the void was the dominant force. Reality, as revealed by the James Webb Space Telescope, is a complete inversion of that image. Instead of grains of sand, we are finding massive boulders appearing instantly in a vacant desert. These are not clusters, they are titans. When we look at the data from the Webb study, we aren't seeing the tentative first breaths of a galaxy. We are seeing fully realized cities of stars possessing a mass and a structural maturity that simply should not exist in that time frame. Consider the sheer density of these systems. In the predicted models of the early universe, the void was supposed to be a place of extreme dilution. Gas was expected to be spread thin, cooling slowly, collapsing only in rare, isolated pockets. But the JWST images show something far more aggressive. The stars in these early galaxies are packed together with a ferocity that defies the old logic. We are seeing stellar densities that make the center of our own Milky Way look sparse by comparison. It is as if the universe decided to compress billions of years of evolution into a few million. If the early universe was a dark room, we expected to see a few distant candles flickering in the corners. Instead, we have walked in to find a series of blinding searchlights, each one powered by billions of suns, casting a glare across the deep infrared. The amount of matter concentrated in these small regions of space is staggering. We are talking about tens of billions of solar masses crammed into a volume of space that, according to every textbook written before 2022, should have been nearly empty. This is not just a difference in size, it is a difference in nature. A small galaxy grows by slowly pulling in gas from its surroundings, a patient process of accretion, but to create a titan in under 700 million years requires a level of efficiency that borders on the violent. The gas had to collapse almost instantly. The stars had to ignite in a synchronized explosion of light. The density of these systems suggests that the early cosmos was not a quiet nursery, but a high-pressure forge operating at a speed that our current physics cannot easily explain. We are observing a structural anomaly that breaks the timeline of the cosmos. In the traditional view, the universe follows a hierarchy. Small things merge to make medium things, and medium things eventually merge to make the giants. But here, the giants are already there, standing alone in the dark before the smaller building blocks have even had time to form. It is as if we found a fully constructed skyscraper in a city where the first bricks had only just been fired. The sheer presence of these massive, dense cores suggests that gravity in the early universe may have behaved with a hunger we didn't anticipate. Or perhaps the dark matter halos that seed these galaxies were far more potent, pulling in vast reservoirs of hydrogen with a force that accelerated the clock of creation. The void, which we thought was a barrier to growth, became a highway for mass. These galaxies didn't just grow, they erupted. When you look at the deep field images, you can see them, small amber-colored smudges of light. To a casual observer, they are just dots, but to an astrophysicist, those dots are screams of contradiction. Each one represents a concentration of mass that challenges the Planck collaboration's 2018 cosmological parameters. Each one is a point of light that says the old rules of time and growth were wrong. We are no longer looking at a slow dawn. We are looking at a sudden blinding flash of maturity. The density of these stars, the weight of these galactic centers, and the impossible speed of their assembly point toward a missing chapter in the history of everything. The universe did not wake up slowly. It woke up with a roar, building empires of light while the rest of space was still cold and silent. And yet, the mystery does not stop at the size of these objects. The more we analyze the light escaping these dense cores, the more we realize that the mass is only the first part of the puzzle. There is something about the way these stars are arranged and the way they burn that suggests a deeper irregularity. This structural anomaly whispers a secret about the nature of time and gravity. This realization forces a quiet shift in how we perceive the architecture of existence. For decades, we viewed the history of the cosmos as a slow, patient climb, a gradual ascent from the simplicity of hydrogen gas to the complexity of planetary systems. We believed the universe operated on a schedule of steady increments, where order was a hard-won prize earned over eons of drifting and colliding. This was the comfort of the old map. It suggested a universe that learned how to build, a cosmos that took its time to master the art of the star. But the evidence from the James Webb Space Telescope suggests a different truth. It suggests that the universe was far more efficient at creating order than we ever dared to imagine. The deep time of the cosmos may not have been a slow climb at all, but a sudden violent leap into complexity, expectation, a gradual sunrise, reality, a blinding flash of maturity. When we speak of the cosmic dawn, the term evokes an image of a soft golden light slowly creeping across a dark horizon. It implies a tentative beginning, a period of hesitation where the first stars flickered into existence one by one, like lonely candles in a vast, empty cathedral. In this version of history, the first galaxies were fragile things, small clusters of stars that spent millions of years wandering through the void before finding enough mass to anchor themselves. We imagined a childhood for the universe, a long, awkward phase of growth and trial and error. The data now tells us that the universe skipped its childhood. The galaxies identified by Labbe and the team in their 2023 Nature paper do not look like the tentative sketches of a beginning. They look like finished masterpieces. They possess a structural confidence, a density of stellar mass, and a gravitational grip that suggests they didn't evolve so much as they erupted. This implies that the mechanisms of creation, the way gravity pulls matter together and the way gas collapses into fusion, were operating at a speed and efficiency that defies our current physics. If these massive systems were already mature just a few 100 million years after the start, it means the window for becoming was nearly non-existent. The universe did not spend its early days experimenting. It moved straight to the endgame. It built cities of 100 billion stars while the clock of time had barely begun to tick. This suggests that the early universe was a place of terrifying productivity. The void was not a wasteland, but a pressurized engine, driving matter into concentrated hubs of light with a ferocity that we cannot replicate in our models. We are seeing the result of a cosmic efficiency that turned the vacuum into a factory. The scale of this leap is almost impossible to process. It is the difference between a seed slowly growing into a tree over a decade and a seed that, the moment it touches the soil, instantly becomes a forest of ancient sequoias. We must now consider the possibility that our understanding of deep time is skewed. We have always measured the age of the universe by the slow decay of elements and the distant shift of light, but these galaxies suggest that the universe has a hidden gear, a way to accelerate the assembly of matter that we have never seen in the modern era. In the current epoch, galaxies grow through slow mergers and the quiet accretion of gas. But in the first few 100 million years, the universe seemed to operate under a different set of laws, or perhaps a different intensity of gravity. This leap into complexity means that the early universe was not a place of emptiness, but a place of extreme congestion. The distances between these massive giants were likely smaller than we thought, creating a crowded, luminous landscape where the first generation of stars burned with a brilliance that would blind any observer. The silence of the void was broken almost immediately by the roar of 1 billion newborn suns. This shift in perspective changes the very nature of our origin story. We are not the result of a long, slow accumulation of matter. We are the descendants of a sudden, explosive burst of organization. The universe did not drift into complexity. It crashed into it. The sheer speed of this process suggests that the drive toward order, the impulse to create stars, galaxies, and eventually the heavy elements that make up our own bodies, was encoded into the fabric of space-time from the very first second. The cosmos was not waiting for the right conditions to emerge. It created the conditions. It forced the hydrogen to collapse. It pushed the gas to the breaking point, and it ignited the darkness with a precision that feels almost intentional. We are looking at a universe that was impatient, a universe that wanted to exist and wanted to exist in its most complex form as quickly as the laws of physics would allow. As we drift further into this realization, the comfort of the slow dawn vanishes. In its place is a landscape of suddenness. We see a cosmos that jumped from nothingness to maturity in a heartbeat of galactic time. This efficiency is the new mystery. If the universe could build massive, stable galaxies in a fraction of the time we thought possible, then the limits of what can happen in the dark are far wider than we ever suspected. The void is not as empty as it seems, and the clock of the universe does not always tick at the same speed. There are eras of acceleration, moments where the cosmos decides to leap forward, bypassing billions of years of expected evolution to reach a state of maturity. We are living in the aftermath of that first great leap. We are the ghosts of a sudden flash, inhabiting a universe that learned how to be complex before it even learned how to be old. And yet, the mystery deepens when we look at the centers of these ancient giants. But as the measurements emerged from the deep infrared, we found that the impossibility of these galaxies was not just a matter of size, but of substance. To understand the true nature of this anomaly, we must look at the chemistry of the stars themselves. In the standard map of the cosmos, the early universe was supposed to be pristine, consisting almost entirely of hydrogen and helium. These are the simple elements, the raw materials of the Big Bang. For anything heavier to exist, for carbon, oxygen, or iron to form, a star must first be born, live its entire life, and then die in a violent supernova. This process is the cosmic forge, and it takes time. It requires generations of stellar birth and death to seed the void with the heavy elements we call metals. Expectation, a slow chemical enrichment over billions of years. Reality, a chemical maturity that appears almost instantly. A 2023 study led by Pierini and colleagues published in the Astrophysical Journal revealed a detail that shakes the foundation of this timeline. When the James Webb Space Telescope looked into the nuclei of these ancient galactic giants, it did not find the simple, pure gas of a young universe. Instead, it detected the unmistakable signature of metal-rich stars. These stars contain heavy elements that should not have had time to exist. They are the children of ancestors that, according to our old clocks, had not yet been born. Here is where you come in, standing at the edge of a chemical paradox. If we see metal-rich stars in the very first galactic nuclei, it means the cycle of stellar death and rebirth happened at a pace that defies our current models. It suggests that the first stars were not just massive, but that they lived and died with a ferocious speed, polluting their surroundings with heavy elements in a fraction of the time we once assumed. We are seeing the residue of 1,000 generations of stars compressed into a window of time so narrow it barely registers on the cosmic scale. Consider the scale of this acceleration. In our current understanding, the transition from a universe of simple gas to a universe of complex chemistry is a long, winding road. But in these early systems, that road was a shortcut. The heavy elements, the iron in your blood, the calcium in your bones, were being forged in the hearts of these ancient titans while the universe was still in its absolute infancy. The machinery of the cosmos was running at 1,000 times its expected speed. This is not a gradual transition. It is a chemical leap. To find such maturity in the first few 100 million years suggests that the early universe possessed a catalyst for complexity that we have yet to name. It is as if we stepped into a nursery and found children who already possessed the wisdom and experience of elders. The metal-rich stars in these nuclei are the evidence of a hidden history, a period of hyper-efficiency where the universe rushed to create the building blocks of complexity. This discovery forces us to rethink the relationship between time and matter. We used to believe that the chemistry of the universe was a slow climb, a steady accumulation of weight and complexity. But the data from the Astrophysical Journal suggests that the universe had a capacity for sudden concentrated bursts of evolution. These first galactic nuclei were not just collections of stars, they were high-pressure laboratories where the laws of chemistry were pushed to their absolute limits. If the first galaxies were already chemically mature, then the timeline of everything that followed is shifted. The window for the emergence of the first heavy elements is no longer a slow dawn, but a sudden flash. We are looking at a cosmos that was not merely impatient to grow in size, but impatient to grow in depth. The presence of these metals tells us that the universe was ready for complexity long before it was ready for stability. It was creating the ingredients for planets, for rocks, and for life, while the light of the first stars was still echoing across the void. The implications are quiet but profound. It means that the potential for complexity is a fundamental property of space-time, not a lucky accident that took billions of years to happen. The drive toward the creation of heavy elements, the drive toward a universe that could eventually support us, was present and active from the very beginning. The metal-rich stars are the fingerprints of this drive, etched into the light of galaxies that have been dead for 13 billion years. We are left with a vision of a young universe that was far more violent and far more efficient than any textbook ever described. It was a place of rapid-fire stellar deaths and immediate chemical rebirths. It was a chaotic, shimmering forge where the elements of our own existence were hammered out in a rush of gravity and heat. We are not the result of a slow, patient process, but the echoes of a sudden, explosive maturity. As we drift away from these ancient nuclei, we realize that the void was never truly empty, and the dawn was never truly slow. The universe did not wake up gradually. It screamed into existence, fully formed and chemically rich, bypassing the expected stages of its own growth. We are inhabiting a reality that was accelerated from the first second, a cosmos that mastered the art of complexity before it had even settled into its own shape. The light from these impossible galaxies has traveled across the expanding dark for billions of years just to reach the golden mirror of the Webb telescope. It is a postcard from a time that should not exist, written in a chemical language that we are only now beginning to translate. The metal-rich stars are the evidence that the universe was always rushing toward us, accelerating through the darkness to ensure that the building blocks of reality were ready. And as these ancient lights fade into the distance, we return to the silence of the present. And yet the mystery of the first galaxies is not merely a question of how they grew, but what lay at their heart. For a galaxy to achieve such impossible maturity in a few 100 million years, it requires a seed of immense power. Here is where we look toward the shadows of the early universe, the invisible giants known as primordial black holes. Expectation, a slow accumulation of gas and dust that eventually collapses into a black hole over millions of years. Reality, the discovery of quasars and supermassive black holes that were already billions of times the mass of our sun, while the universe was still in its infancy. In a 2023 study published in the monthly notices of the Royal Astronomical Society, researchers led by Webb explored the existence of these massive systems. The data suggests a terrifying efficiency. These are not the small stellar mass black holes we see in our own neighborhood, but monsters that emerged almost instantly. To understand this scale, imagine a seed that does not grow into a tree over decades, but instead erupts into a full-grown forest in a single heartbeat. The James Webb telescope has captured the light of these early quasars, reveals that they were consuming matter at a rate that defies the standard limits of accretion. They were the engines of the early cosmos, spinning with a violent energy that illuminated the surrounding hydrogen fog, carving out bubbles of transparency in a universe that was once a blind, opaque wall. If we were to, scale the observable universe down to the size of the Earth, these early supermassive black holes would be like needles of infinite density, yet their gravitational reach would warp the fabric of space around them for thousands of miles. They did not just exist within these first galaxies. They likely dictated the growth of the galaxies themselves. The black hole and the galaxy grew in a symbiotic dance, a locked rhythm of consumption and expansion, but as the measurements emerged from the JWST deep field analysis, a new paradox appeared. These black holes were too large for the amount of time available since the Big Bang. According to the standard model provided by the 2018 Planck collaboration, there simply was not enough time for a star to die and a black hole to grow to this size through normal means. This suggests a different origin. Perhaps these were not born from stars at all. Some theories now propose the existence of direct collapse black holes, where massive clouds of primordial gas bypass the stellar stage entirely, collapsing directly into a singularity. A sudden catastrophic birth that skipped the childhood of a star and leapt straight into the adulthood of a monster. We are looking at a universe that was far more aggressive and efficient than our models ever predicted. The early cosmos was not a quiet nursery, but a forge of extreme gravity and blinding radiation. These primordial seeds created the first structures, pulling the scattered hydrogen into the first spirals, the first ellipsoids, and the first great cities of stars. The scale of this process is a reminder of how little we know about the first few moments of existence. We are seeing a history that was written in a language of gravity and light, a record that the universe filed into space-time itself. We drift now through the realization that the void was never truly empty, but was filled with these invisible anchors, pulling the chaos of the Big Bang into the order of the galaxies we see today. And yet, as we drift further into the infrared depths, a second anomaly emerges from the data, one that challenges our understanding of how the first light actually behaved. For decades, the consensus was that the early universe was a place of slow, gradual awakening. Expectation, a long period of darkness known as the cosmic dark ages, where the first stars flickered to life one by one, like distant candles in a vast, cold cathedral. Reality, a sudden and violent surge of luminosity that suggests the universe woke up all at once. This shift in understanding comes from the 2023 study led by Labbe and his team, published in Nature. Their analysis of the James Webb data revealed a population of candidate massive galaxies existing only 500 to 700 million years after the Big Bang. To put this in perspective, if the entire history of the universe were a single calendar year, these galaxies appeared in the final hours of December, yet they already possessed the mass and complexity of galaxies that should have taken billions of years to evolve. They are not the fragile, chaotic clumps of gas we expected to find. They are massive, structured, and heavy with old stars. Imagine the scale of this impossibility. If we think of a galaxy as a city, the old models predicted that the early universe would be filled with small, primitive villages of a few thousand stars. Instead, the JWST has found sprawling metropolises, cities of stars so dense and so bright that they defy the laws of cosmic growth. It is as if we traveled back to the dawn of human history and found a modern skyline of steel and glass standing in the middle of the Pleistocene. This discovery forces us to look at the relationship between dark matter and visible light in a new way. The 2023 research by Pierini and colleagues in the Astrophysical Journal suggests that the efficiency of star formation in the early cosmos was far higher than anything we observe in the modern universe. In the current epoch, galaxies are careful with their fuel, converting gas into stars over eons. But in the beginning, the universe seemed to be in a rush. The gas did not just drift, it crashed together with a focused intensity, fueling a starbirth rate that is nearly impossible to replicate today. This means the early universe was not a quiet nursery, but a high-pressure furnace. The stars that formed during this era were likely different from the ones we see now. They were massive, blue, and short-lived, burning through their fuel with a desperate hunger, flooding the void with ultraviolet radiation before exploding in spectacular supernovae. These first stars were the architects of the cosmos, forging the first heavy elements, carbon, oxygen, and iron, and seeding the vacuum with the building blocks of everything that would eventually become us. Here is where the paradox deepens. The sheer mass of these early galaxies, as documented in the monthly notices of the Royal Astronomical Society by Duane and his team, suggests that the universe was capable of concentrating matter far more rapidly than our current gravity models allow. We are seeing a universe that skipped its own childhood. We are seeing a cosmos that arrived at maturity with an efficiency that borders on the impossible, leaving us to wonder if our map of time itself is missing a crucial piece. As we contemplate these ancient cities of light, we realize that the early universe was a place of extreme contrasts. It was a void of absolute cold, yet it hosted the hottest, most violent births of stars in history. It was a sea of hydrogen, yet it produced the complex chemistry of life almost immediately. We are floating through a history where the laws of physics were pushed to their absolute limits, creating a landscape of light that we are only now beginning to perceive. The blinding radiance of those first galaxies, those impossible titans of light captured by the golden mirror of the Webb telescope, begins to recede. We are drifting away from the searing heat of the cosmic dawn, leaving behind the chemical forges and the massive stellar cities that defied every map we once drew. The intense amber glow of the early universe, which pushed the boundaries of the possible, slowly softens. It fades from a brilliant white to a deep muted gold, then to a bruised purple, and finally it dissolves into the velvet dark of the deep void. This transition is not a loss, but a return. We are moving from the chaotic energy of a universe screaming into existence back into the restorative silence of the present. The scale of 13 billion years, the weight of 10 billion suns, and the paradox of an accelerated maturity now settle into the background, becoming a quiet hum in the vastness of space. The noise of the Big Bang has long since cooled into the cosmic microwave background, a gentle, invisible warmth that wraps around everything in existence. As we drift further from the edge of the first light, The tension of the impossible begins to dissolve. The mind, which struggled to grasp the sheer density of those early galactic nuclei, can now let go. The heavy elements, the metal-rich stars, and the shattered remnants of the first stellar generations are all held safely in the archives of space-time, filed away in the long memory of the vacuum. There is no longer a need to solve the puzzle, no need to reconcile the expectation of a slow dawn with the reality of a sudden flash. The darkness here is different from the darkness of the early void. That was a darkness of anticipation, a cold fog of hydrogen waiting for the first spark. This darkness is a blanket. It is the quiet of a cosmos that has already found its shape, a universe that has spent billions of years expanding, cooling, and creating the very atoms that now allow us to witness it. We are floating in the deep infrared, where the only sound is the rhythmic expansion of the universe, a slow and steady breath that carries us toward an infinite horizon. The light of those ancient galaxies continues its journey, crossing the light years to reach our sensors, but for now, we let that light slip away. We sink deeper into the velvet black, where the distance between stars becomes a sanctuary. The complexity of the early universe, the violence of its efficiency, and the mystery of its sudden maturity are now just distant echoes, flickering like dying embers at the edge of our vision. In this stillness, the scale of the cosmos no longer feels overwhelming. It feels like a homecoming. We are small, yes, but we are made of the very metals that Pierini and the teams at the Astrophysical Journal found in those first impossible nuclei. We are the living evidence of that ancient rapid-fire chemical rebirth. The iron in our blood and the calcium in our bones were forged in that same rush of gravity and heat billions of years ago, in cities of stars that existed before the universe had even settled into its own skin. We are not separate from the mystery. We are the mystery observing itself. The distance between the first light and the current dark is not a gap, but a bridge. As we glide through this bridge, the weight of existence grows lighter. The questions of how and why the first galaxies grew so large so quickly can wait. They are etched into the light, preserved in the deep field analysis of the Webb telescope, waiting for us to return to them when we wake. The restorative darkness now closes in, a soft obsidian tide that washes away the remnants of the journey. The blinding brilliance of the early universe is now a memory, a single point of light disappearing into the distance until it is gone entirely. There is only the void now, but it is a warm void, a supportive silence that invites the mind to stop searching and start drifting. We are floating in the center of a great cosmic peace. The expansion of space carries us gently away from the friction of thought and the effort of understanding. The universe is vast, and we are a part of its slow, inevitable unfolding. The impossible scale of the first galaxies is now just a dream of light, a ghost of a time when the cosmos was young and restless. Now it is time for the restlessness to end. As the last shimmer of the infrared spectrum vanishes, we are left with the absolute quiet of the deep. This is the place where the laws of physics become a lullaby, where the curvature of space-time feels like a cradle. The journey to the edge of the first light has brought us back to the simplicity of the now, to the quiet breath of a body at rest, in a universe that has always known how to provide a place for sleep. If the first galaxies were already mature at the dawn of time, if they bypassed the slow growth we expected and leapt straight into complexity, does that mean the universe possesses an inherent drive toward life and consciousness that we have yet to fully name? Sleep well tonight, and tomorrow we will continue to explore the deepest mysteries of the cosmos as you subscribe to our shared journey.